Imagine a giant trampoline. Not just any trampoline, but one that stretches across the cosmos, vast and boundless. This trampoline represents the fabric of space and time, an intricate and flexible web that holds the universe together. Now, place a bowling ball in the center. This ball symbolizes a massive object like a planet or a star. What happens? The ball creates a dip, right? This dip is a distortion in the fabric of the trampoline. That's similar to how massive objects like stars and black holes warp the fabric of space-time, creating gravitational wells. Space-time is not just an empty stage where cosmic events unfold. It's a dynamic entity, constantly interacting with the matter and energy within it. It's an active player, bending and curving under the influence of gravity, shaping the paths that objects follow. This curvature is what we perceive as gravity. It's the invisible force that governs the motion of planets, stars, and galaxies. It's the reason Earth revolves around the sun, and why we stick to the ground instead of floating away. Gravity is the glue that holds the universe together. Think of it this way. Imagine rolling a marble across the trampoline. The marble represents a smaller object moving through space-time. If it's far from the bowling ball, it will travel in a straight line, unaffected by the dip. But if it gets close, it will curve inwards, pulled by the dip created by the bowling ball. This is the essence of gravitational attraction. This is analogous to how objects move under the influence of gravity. They follow the curves in space-time created by massive objects. This cosmic dance is the foundation of our universe's structure and behavior. For centuries, we thought of gravity as a mysterious force acting across vast distances. Then came Albert Einstein with his revolutionary theory of general relativity. Einstein said gravity is not a force, it's a consequence of the curvature of space-time. This curvature is what we experience as gravity. The more massive an object, the more it warps space-time and the stronger its gravitational pull. That's why light, even though it has no mass, bends around massive objects. It's simply following the curvature of space-time. Now, imagine an object so incredibly massive, so unbelievably dense that it actually punches a hole in the fabric of space-time. That's a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Black holes are born from the death throes of massive stars. When these stars exhaust their nuclear fuel, they collapse under their own gravity, imploding into an infinitesimally small point called a singularity. The singularity is the heart of a black hole, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. Imagine the event horizon as a boundary in space-time, a threshold that marks the edge of a black hole. Cross this boundary and you're trapped forever, unable to escape the immense gravitational pull. Not even light, the fastest thing in the universe, can escape the clutches of a black hole once it crosses the event horizon. This makes the event horizon a fascinating yet terrifying concept. Think of it this way. Imagine trying to canoe against a current. The stronger the current, the harder it is to make any progress. If the current is strong enough, you'll never be able to get back upstream no matter how hard you try. The event horizon is like a cosmic current, except instead of water, it's gravity pulling everything inwards with an unstoppable force. The event horizon is not a physical barrier you can touch or see. It's simply a point of no return, a boundary beyond which escape is impossible. If you were to fall into a black hole, you wouldn't feel anything special as you crossed the event horizon. It would be just like crossing an invisible line. But from that point on, your fate would be sealed, and there would be no turning back. You would be inexorably pulled towards the singularity, where the gravitational forces would crush you out of existence, ending your journey in the most extreme way possible. Here's where things get really strange. Einstein's theory of relativity tells us that gravity not only warps space, but also time. The stronger the gravity, the slower time runs. Imagine two identical clocks, one on Earth and one in orbit around a black hole. The clock near the black hole, where gravity is stronger, will tick much slower than the clock on Earth. This phenomenon is called time dilation. It means that time is not absolute, but is relative to the observer's reference frame. Time dilation has been experimentally verified, and it's a crucial factor in the functioning of satellites orbiting our planet. As we dive deeper into the mysteries of black holes, let's ponder an intriguing question. What would happen to time as you approach the event horizon? Imagine you're an intrepid explorer, bravely venturing towards this boundary where the gravitational pull becomes irresistible. Assuming you were alive and somehow protected from the extreme forces, your perception of time would undergo a dramatic transformation. From an external observer's perspective, it would appear as though you were slowing down, almost coming to a standstill as you neared the event horizon. This is due to the intense gravitational time dilation at play. To them, your journey would seem to stretch on indefinitely, as if time itself were grinding to a halt. But how would you, the explorer, experience this phenomenon? Remarkably, from your own viewpoint, time would continue to flow normally. You wouldn't notice any slowdown. Every second, every heartbeat would feel just as it always had. This paradox is a testament to the relativity of time. As you approach the singularity, the point of infinite density at the black hole's core, the warping of time would become even more extreme. The closer you get, the more the concept of time as we understand it begins to break down. But does time stop at the event horizon? For you, the answer is no. You would continue to experience time in a linear fashion until you reach the singularity. However, for an outside observer, it would appear as though you were still at the edge of the event horizon, a ghostly image suspended in space. This mind-bending scenario challenges our fundamental understanding of time and forces us to confront the limits of human comprehension. It serves as a poignant reminder that the universe is far stranger and more complex than we can ever imagine. Now let's explore how these cosmic puzzles have practical implications in our everyday lives. Take GPS, for example. The global positioning system, which we rely on for navigation, timing, and even some financial transactions, wouldn't be as accurate without considering the effects of time dilation. GPS satellites rely on precise timekeeping to determine your location on Earth. These satellites orbit our planet at high altitudes, where the effects of gravity are weaker than on the surface. But because these satellites are in orbit, they experience time dilation. Time runs slightly slower for them compared to clocks on Earth, about 38 microseconds per day. This discrepancy, though minuscule, can lead to significant errors in positioning if not corrected. To compensate for this, GPS satellites have to factor in the effects of time dilation to ensure these corrections are made, allowing us to navigate with pinpoint accuracy. Without this correction, our GPS systems would soon be off by several kilometers. Imagine the chaos in navigation, logistics, and even emergency services. Black holes are not just fascinating objects of scientific curiosity. They're essential to our understanding of the universe and have practical implications that reach into our everyday lives. They push the boundaries of our understanding of the universe and challenge us to confront the limits of physics as we know it. By studying black holes, we not only learn about the cosmos, but also improve technologies that we use daily. Black holes are a testament to the strangeness and wonder of the universe we inhabit. They are regions where gravity reigns supreme, warping space and time in ways that defy our everyday intuition. These cosmic objects are a constant reminder that the universe is far more bizarre, far more wondrous, and far more awe-inspiring than we could ever have imagined. As we continue to explore the cosmos, we can only marvel at the mysteries that await us, mysteries that challenge us to expand our minds and embrace the sheer strangeness of reality. If you enjoyed our video, please help us out by giving it a thumbs up and sharing. Why not check out one of the 2 other videos of ours that are on your screen now?